So in 6.8 we have graphing radical functions. Now we're not going to do every radical function, but we definitely want to get a feel for square roots and cube roots as we talk about radical functions. So we're going to graph square root and other radical functions. A lot of our time today is probably just going to be spent on graphing those square roots as we go through this. So the formula, it says A equals pi r squared. Area of a circle shows that the area is a quadratic function of the radius of the circle. We have a square term. And a degree 2 is what that's called. And degree 2 polynomials are quadratics, and the graph has parabolas. And we see that the formula r equals 1 over the square root of pi square root of a shows that the radius of the circle is a square root function of the area. They just made that really weird. They really did. We did this yesterday. When you're working with word problems, you don't swap the variables. It wouldn't make any sense to say area is the same as the radius. Their units aren't even the same when you label them. So what we do instead is we go ahead and divide by pi, and then we take the square root. And that's the same thing they have up here. They just manipulated it a little too much. So what they want us to see is, when we're working with quadratics, the inverses, they're going to be square roots. They are. So we have to have an understanding of what those will look like and kind of get a visual in our head whenever we see something that has a square root involved in it. So square root, inverse of a quadratic function, has to have a restricted domain. As I went through the homework and I talked about the parabolas, there are a lot of y's you don't use when you're graphing a parabola. A parabola has a vertex, and that vertex cuts off what y's you're using. So if you have a positive x squared, you're using all the y's that are above that vertex. If you have a negative x squared, you're using all those that are below that vertex. And so that means it has a restricted domain. Because it's the inverse, the range of the first one becomes the domain of the second. A horizontal line can intersect the graph of y equals x squared, or f of x equals x squared in 2 points, where f of negative 2 equals f of 2. So right here they're saying if we draw a horizontal line, we'll see that for this parabola, it's going to hit in 2 distinct spots. Now, at first glance, you're like, well, we had the vertical line test before. What do we care about a horizontal line test? If vertical line tests are what we use for normal functions, or their inverse, we would have to use the horizontal line test. So if we have this graph, y equals x squared, and we use the horizontal line test, it's going to fail because we are hitting 2 distinct spots. What that tells us is its inverse is not a function. And we can see this. This is its inverse. So kind of a sideways opening parabola. That definitely is going to fail the vertical line test. So what we know is this. We know how to graph parabolas. We could use the horizontal line test immediately on those parabolas and know the inverse is not going to be a function. It just isn't going to work. So we have a horizontal line test and a vertical line test. Horizontal line test is for inverses, and vertical line test is for our normal functions. So thus a vertical line can intersect the graph of f inverse in 2 points. F inverse, not a function because it fails the vertical line test. And if we want to work with functions, which by the way we really like functions, we talked yesterday about how if it's a one-to-one function, that's a really big deal. There's a lot of math you can do with one-to-one functions. What we would have to do is say, you know what, I'm not going to be able to use all of this. Because if I use all of it, it's not a function. But if I don't use this part of it, if I just use the positive part of this function, then it's a function. Or if I just use the negative portion, then it's a function. I just can't use both at the same time. So what they're saying in this box here is we can restrict the domain so that we do get a function out of this if necessary. And that's just one of the things that generally we're going to have to do if we want to work with functions. So if you take a look at this, you can see we would say, okay, I need the top portion of the square root of x. If I need just the top portion of that, what does my original function need to look to make that its inverse? Well, we can't use the whole parabola. We'd have to say just use the portion of the parabola that's to the right of the y-axis, and that's where x is greater than or equal to 0. So this would be a restricted domain of f, which would become the range of f inverse. Sense when you see the visual. We had to restrict things here so that we could just get one portion, one branch of that square root function, not the whole thing. So sometimes we have to restrict domains to make sure that we're getting a function that we can work with. All right, inverses of the power functions y equals x to the n, if we restrict the domains as needed. Sometimes we'll need to do that, sometimes we won't. They will give us y equals the nth root of x, and those will be families of radical functions. So we'll have a family of square root functions. We'll have a family of cube root functions. That's as far as we're going to go. We will talk a little bit about, fourth root and sixth root and all of that. But what we've learned in the past is that all of the even degree polynomials behave the same. So all of the even radical families behave the same. And all of the odd functions, degrees that we looked at before, behave the same. It's going to be the same with the inverses. So if we know what the even powers do and we know what the odd powers do, they're all going to behave the same way. So it says, in particular, f of x equals the square root of x is the parent for the square root function. So this little bugger right here is the parent. That's where we start. But from there, we know things are going to happen. We're going to have reflections over the x-axis. We're going to have vertical stretches and compressions. We're going to have to move this right and left, up and down. And this is the monster we really want to get used to right here. Because that's our generic formula that covers any square root that we can get into that form. Y equals a square roots of x minus h plus k. So that'll help us with our square roots. So key concept here, we're going to have families of radical functions. Again, those families will be the square root functions and the cube root functions. So your basic parent is, no bells and whistles, square root function, y equals the square root of x. But we also know when they throw numbers in there, when they throw negatives in there, it affects the graph. It does. So the first thing they're showing us is, if you reflect in the x-axis, you're actually going to see a negative in front of that. And then, if we have a stretch or a shrink, well, that's going to come from a number in front there. Hopefully you remember, if a is a value that's bigger than 1, you're vertically stretching it. And if a is a fraction between 0 and 1, then we're going to vertically compress it. We're squishing it down. Translations, h and k. H is responsible for that horizontal. And remember, whatever you do with x, you always have to think opposite. So if it's x minus 3, that means it moved 3 to the right. So x's are always the opposite of what we see. But the k value, the y, is very straightforward. If it's positive, it's up. If it's negative, it's down. And then over here, instead of just focusing on cube root, they're saying, what if it's any radical? Cube root, fourth root, any index that we have here. We're going to treat it the same way if we can get it in this form. We can get it in this form. So if you put it all together, we've got the a, the h, and the k. And this is just a breakdown of what each of those is going to be as we go through it. All right, so right off the bat, we're going to talk about translating a square root function, translating this vertically. And it says, what are the graphs of y equals the square root of x minus 2 and y equals the square root of x plus 1? Well, the first thing I want to do is figure out the shape. What's the shape of the graph? Well, the shape just comes from the square root of x. Now, normally we'll take a along with it, so we'll have a square roots of x, but this one doesn't have an a other than 1, so there's no change in that shape. And then we'd say to ourselves, self, we know some stuff about square roots. We've been talking a lot about how I can't put numbers in there. So I'm going to have to make sure my x's are greater than or equal to 0. And I want to take the square roots. So yeah, I'll put 0 and 1 in there because those are nice and easy. Square root of 0 is 0, square root of 1 is 1. But I don't want to put 2 in there. 2 is a miserable decimal when you take the square root. I don't want to put 3 in there either. So the next one we would go to is 4. And say, oh good, that's 2. Keep thinking. 5, 6, 7, 8, ooh, 9. That would give me 3. That's our parent function right there. And so this is not an actual graph of what we're going to do. We need to make sure this is dashed or dotted when we graph it, but it's the shape that we need. So we go over here and do our 0, 0, 1, 1, 4, 2, and 9, 3. And like I said, dashed or dotted. For me, it's a little easier up here just to make the dots. Now I want you to switch colors. If you need to, grab some colored pencils out of that bag. Because what we want is for our brain to see, hey, that's the shape. But look what happens when we put a -2 behind it. Look what happens when we put a +1. So take a second and get some colored pencils out of the bag if you need to. Or if you have a pen along with or something, that's always kind of difficult because the erasing a different color to make it kind of pop. Anybody need help? We haven't used them in a while. Maybe they're twisted. Here's this. You should take it out because if it rips, then I have to sew it.
Oh, I got it.
I sew because I have to. I don't sew because I like it.
There, got it. Who's 5 years old?
I made them.
Oh. They're probably so funny that moment.
All right, you ready? Changing colors. Here's what I have to think. Is that an H or a K? I mean, I already have the shape. Well, it's not with the X underneath the radical, so it's not an H, it's a K. This is an up or down, and this is going down too. So I have to take this graph, and I have to move it down too. Well, good news, we already have the graph shape over there. All we have to do now is count 2 down. So we'll pick a few points that were nice out of this, and we'll just count 2 units down. And now that one I want to make solid because that is a final graph. But notice how I color coded it. You could either circle y equals the square root of x minus 2 in the same color. So when you look at this later, you go, oh, right. All we did was count 2 units down. So different color. Where are we moving that one? That's it. Up 1. So you go back to the original, which was our shape, and you move everything up 1. Piece of cake. Why is it a piece of cake? Because we had the shape. We knew what the square root of x looked like. Now, if in the future it's not just the square root of x, let's just say they give us something like this: y equals -3 square roots of x minus 2 plus 4. That's not how we start. There's a lot going on there. We take this in pieces. So what we do is we make a table of a square roots of x, because that's what's responsible for the shape. Once we have that shape, the rest of this is counting. We'll move it 2 to the right and 4 up. Always take a with the shape. That's what we want to do. So down here, boy, it'd almost be easier to just go back up on that one, but we don't have enough color. So we already have our table. Let's get the shape on there, because again, it's just y equals the square root of x, y equals the square root of x. So 0, 0, 1, 1, 4, 2, 9, 3. Color code again. Y equals the square root of x plus 2. Where's that going? Up 2. That's it. Take our nice points and move them up 2. And if you're saying, well, where are the nice points, Cedar Home? They're the points from the table. 0, 0, 1, 1, 4, 2, 9, 3. That one's done. Y equals the square root of x minus 3. Where's it going?
Down
3 down. Yep. 1, 2, 3. Back to the original shape. Down 3. This is generally the point where people go, why didn't we do this first before we did yesterday's? They want you to get a feel for it first. Okay, these all seem to graph this way. What's going on with them? Well, hopefully you're saying this isn't too tough, but remember we don't have a new A value yet, and that's not going to be tough either. It's just that it's different, you know, it's different. So now, I look at this one, and I'm hoping this is super easy, like the last one, right? The only way to know that is to know what A is. Is A still 1 in this?
Oh, you betcha.
We're using that same shape, same table. 0, 0, 1, 1, 4, 2, 9, 3. But that's not K we see anymore. How do we know? Under the radical. So it deals with x, which means we have to think opposite. X is right and left. Which way is this supposed to go? Exactly. 4 to the left. With 4 to the left. That's usually the part we forget with time. That H always have to take opposite. Because it's X minus H in the formula. We switch colors, which you probably have already done. Where's that second one going? Back to the original and move everything to the right 1 unit. Gotta get harder at some point. Not yet. See a new A value? Me either. Starting to memorize 0, 0, 1, 1, 4, 2, 9, 3? Yeah, you can't help it. Just do. Y equals the square root of x minus 3. Where are you moving it, everybody? Switch your colors. Square root of x plus 2, where's it going? That's bad, right? It's all about that parent. If you know what that parent is doing, then it's just a matter of counting. Cool. Well, like I said, eventually, you know, we got to have an A value that's not going to be the same. But this says, recall from lesson 2.7 that for any transformation, AF, x minus h plus k of the parent function, f of x, A indicates a vertical stretch or shrink. What's up with the F, Cedar Home? They're trying to show us that this is the original function, and we're putting a different A value in front. It's actually kind of the worst way to think about it, because what we want to do is think shape first, and A is responsible for the shape, so that's what we need to use. So similarly, for the combined transformation, y equals a square roots of x minus h plus k. A is a vertical stretch. If A is a number, bigger than 1. Again, don't think positive or negative. That's responsible for a reflection. And then if we have a fraction between 0 and 1, then we have a compression. Negative value, reflection over the x-axis. So let's see what we can do here. I would like this problem to be just as doggone easy as the problem we were doing. Well, it's not going to be too bad. Because here's what we do. We think back to what we already know. Like so. That was the shape when there was no a value. And I realize if I want to know what the shape is for this graph, I'm not taking h and k along for the ride. They're not responsible for shape. They are just responsible for shifting the graph, right, left, up, and down. So what I have to do is this. I need to know what's going to happen for negative 1/2 square roots of x. Now, how is this helpful? Because we already did the square root of x. That means all we have left is taking all of these times the negative 1/2, and we'll have the new shape. So 0 times negative 1/2 is still going to be 0. 1 times negative 1/2 will be negative 1/2. 2 times negative 1/2 will be negative 1. 3 times negative 1/2 will be negative 1.5. That's the shape of this graph. So that's the one that's dashed or dotted. So we've got 0, 0, 1, negative 1/2. And some of you, so this isn't confusing, might want to do this. I'm just going to cross off that middle one because it wasn't done when we found the square root of x. We also had to take it times the negative 1/2. 1, negative 1/2. 4, negative 1. And 9, negative 1.5. You can definitely see this one's been compressed. I mean, that's what that 1/2 is doing, it's compressing it. We can definitely see that this flip-flopped from the top of the x-axis down. So this is the shape of our new graph. And now all we have to do to finish this up is figure out where to move it. So where should we count to get our correct location for this graph? Right 3 and up 1. So we'll take each of those points that we just graphed and we'll move it right 3 and up 1. So it's really important that those numbers of 0, 0, 1, 1, 4, 2, 9, 3 come to you very quickly, because then this isn't going to take long at all once you have those. It's just a matter of counting to get it to its new position. Interesting. Domain range. Domain is the x's. I think we already know this, because this would all depend on a starting point. Didn't we just say we had to go 3 and 1 to get to this point? So wouldn't that make that the ordered pair, 3, 1? What's the x? 3. Are we going right forever or left forever? X is greater than or equal to 3. We've got the visual. What's our first y value? We going up or down with our graph? Starting point. In square root graphs, we're going to have a starting point. That's where our x and our y's begin. That's what we want to show. Alrighty. Different a value, but at least it's not fraction, right? In order to get my shape graph, what do I have to do to these values? That's it. That's all we have to do. Our shape comes from a and the square root of x. So that's the piece we need to get our shape. So that one will go on our graph. Again, you're going to ignore the middle piece. That was a portion of our thinking, but not a portion of our graphing. So 0, 0, 1, 3, 4, 6, and 9, 9. Everybody see the vertical stretch? Hard not to, right? Yeah, there's our vertical stretch. And I don't think I'm going to put a lot more dots on that one because I want to know where those points are so when I move them, I can be accurate. So then the next piece is, where are we going with it? 2 left and 4 down. It's just counting from here. That's all it is. 2 left and 4 down. Since I see that little domain and range thing down there, I probably want to figure out where that new starting point is. Well, you just told me where it was. It was 2 left and 4 down. That's where it was. So we're going to have something with x and -2. And we're going to have something with y and 4. Take a look at our graph, the green one. Have up there. Are we going to the right or to the left with the x's? Take a look at the y's. Up or down? Got it. There it is. So shape, then use your H and K to figure out where you're going to go. Justin.
Oh wait, never mind.
Thinking backwards?
It's -4, not 4.
Yeah, that's right.
Oh, did I just put 4? Thank you. In a negative. There we go. Thank you, thank you, thank you. All right, I suppose I'm getting close and I did not get that. Which example are we on? Guess that's a good place to stop us any there. We'll just call it 43210 me. No, obviously when you came in, not so steady with square roots, but how are you feeling about graphing square roots? Good, good, good. Okay, so here's what I'll do. I'll get the assignment up here, and then I will yak at you a little bit about the extra credit piece.
Yes. Very little.
Well, do you think you need more?
No.
No.
Don't need a whole lot, right?
It's a graph.
But yeah, graph paper again is in the wire baskets over there. Alrighty, so now the extra credit. There is a video already on Schoology for the extra credit, and it's just a mini lesson on the Pythagorean theorem and your special right triangles, which of course, hopefully some of you remember the song now. 30, 60, and 90, it's easy to see. The short side is 1 down and back, 2. The other side is a square root of 3, and it's 45, 45, 90 equal. These are easy to get. Or it's 1, 1, square root of 2 in the triangle game. So this first one is just for you to be able to follow along with the notes as you watch the video.
Field nurse. No way here. What's it called?
So you might want to write at the top of that one. That one's for notes. As you watch the video and follow along, write down the math. Okay.
Oh my gosh.
Okay, so write notes on that one. That one is for you to take notes as you watch the video. This next one is what you'll get points for, but they have to be correct. So don't think, oh, I'm not gonna watch the video. I'll flip through this if I don't get them right. Yeah, here, because here's the deal. I'm gonna give you test points for this.
Oh.
Test points.
How many test points?
And you guys know, that's the big deal, because that's 75% of your
How many
grade.
test points?
Looking at this packet, I would say probably 2. Maximum of 2 test points, depending on what you get right.
Yeah, I'll take one of it. That's
Why don't we just make it up?
so. I'll take it. Yeah, we don't even have that. I mean, the
When does this due?
Let's make it a week from today.
Oh, for sure.
I'll turn it in tomorrow, all done.
I'm so doing.
I just said 100%.
I'll do it. You get to do both.
Let's tell Eli what the first packet was for.
No.
Notes!
Oh.
Hey, it's okay, don't worry. You don't need to say it.
You didn't. Yeah.
Use that nod maybe.
Alright, so the first packet, you're gonna watch the notes, you're going to write down, all the math and good stuff that you get from that. And then the second one is the assignment due a week from today, which would be, oh my goodness, putting us into March. March 3rd.
Oh, boy.
If you get a chance to do it over the weekend, do it over the weekend.
Oh, she will.